Hello friends! Have you ever noticed how some apps run perfectly fine when you first open them, but after a few hours they start lagging, freezing, or eating up your entire RAM until you're forced to restart? That's not random. That's almost always a memory leak. In this video, let me show you what a memory leak actually is, why it happens behind the scenes, and why even apps built by huge companies sometimes slowly die because of it. Let's get into it. Alright, before we talk about leaks, let's quickly understand what memory even means here. When you open any app, a browser, a game, a video editor, it asks your computer for a workspace in RAM. Think of RAM as a giant grid of small boxes. Every photo you load, every browser tab you open, every document you edit, takes up some of these boxes. When you close that photo or that tab, the app is supposed to give those boxes back so other things can use them. That returning part, that's the whole game. And that's exactly where memory leaks begin. Now let me show you how memory is supposed to work. Every app follows a simple three-step cycle. Step 1. Request. The app tells the operating system, hey, I need some memory to hold this image. Step 2. Use. The app does its job with that memory, shows the image, edits it, plays the video, whatever. Step 3. Release. Once the app is done, it tells the system, I don't need this anymore, take it back. That's the healthy cycle. Request, use, release. As long as this loop keeps closing properly, your app stays fast, and your RAM stays free. But what happens when step 3 quietly stops happening? That's where things start to break. So here's the actual definition. A memory leak happens when an app requests memory, uses it, but then forgets to release it. The memory is no longer needed, but the app is still holding on to it. Look at the two sides. On the left, a healthy app. It uses what it needs, frees the rest, and there's plenty of room to keep working. On the right, the same app. But every time it finishes a task, a few memory cells stay locked. The app doesn't even know they're locked. It just moves on to the next task, locks a few more, then a few more. The memory is technically in use, but nothing is actually using it. That's a leak. It's not a crash. It's not an error message. It's just memory that quietly stops coming back. Let me make this real with an example you've actually felt. Imagine a photo gallery app. At 10 a.m., you open 3 photos. The app loads them into memory. Totally normal. A few minutes later, you close those photos and open 3 new ones. You'd expect the old 3 to be wiped from memory, right? But because of a bug, the developer forgot to write the code that releases them. The app loaded the new photos on top, but the old ones are still sitting there. By 10:30, you've scrolled through 50 photos, and every single one is still occupying memory, even though you closed them ages ago. This is exactly the kind of bug that makes Chrome eat 8 GB of RAM after a long browsing session, or makes a video editor slow to a crawl after editing for an hour. The app isn't doing more work, it's just dragging around everything it should have thrown away. Now here's the scary part. Leaks don't announce themselves. They build up silently. In the first minute, you won't notice anything. The leak is small. By minute 30, the app feels just slightly less snappy. Maybe a tiny lag when you switch tabs, but nothing alarming. 2 hours in, the freezes get longer. Animations stutter. Your laptop fan spins up. And eventually, the app either crashes, or your operating system kills it to save itself. This is exactly why apps slowly die. The bug was there from minute 1, but it only became visible when memory ran out. That's also why memory leaks are so hard to catch. By the time the user complains, the original cause happened hours ago. So why does this even happen in code? It comes down to 2 worlds. On the left, languages like C and C++. Here, the developer is fully in charge. When they request memory using something like malloc, they must manually call free when they're done. Forget that one line, and that memory is leaked for the entire run of the program. On the right, languages like Java, Python, and JavaScript. These come with a garbage collector, basically an automatic cleanup system that watches for memory nobody is using and throws it away. Sounds foolproof, right? Not quite. The garbage collector only cleans up memory that has 0 references pointing to it. If your code accidentally keeps a reference alive, say an object stuck inside a list you forgot about, or an event listener that never got removed, the collector thinks it's still needed and leaves it alone. So even with automatic cleanup, leaks still happen. The mechanism changes, but the bug doesn't disappear. Alright, so how do developers actually catch these leaks? They look for one specific pattern, a memory graph that only climbs. In a healthy app, memory usage goes up when you do something, then comes back down when you're done. It breathes. In a leaking app, it just keeps climbing. Up, up, up. never down. That stair-step shape is the fingerprint of a leak. To find them, developers use tools that record memory usage in real time. If you're a web developer, Chrome DevTools has a built-in memory profiler. You can take snapshots before and after an action and see exactly which objects didn't get cleaned up. For C and C++, there's Valgrind, which tracks every allocation and tells you exactly which lines of code requested memory that never got freed. Most modern languages and IDEs have their own profilers too. The tools differ, but the goal is the same: find the memory that went in and never came out. Alright, let's wrap this up. A memory leak is simply memory that an app requested, used, and then forgot to release. The app keeps running, but it keeps holding on to stuff it no longer needs. Over time, this is why your browser feels heavier after hours of use, why some games stutter after long sessions, and why even apps from billion-dollar companies slowly die until you restart them. It happens in languages where developers manage memory by hand, and it happens in languages with automatic cleanup too, just for different reasons. The next time an app starts crawling for no obvious reason, you'll know exactly what's probably going on under the hood. If this video made the concept click, hit that subscribe button and smash the like. It genuinely helps the channel. I'll see you in the next one.